So a quick look at our schedule. Quiz 3 is the next thing that's going to be due. It's due a week from today. And I'm not going to see you Monday because it's a long weekend. So I made sure to get it to you today because I didn't want you to be bored. So you're welcome. So that's your next thing that's due is quiz 3. Project 4 is due the following week on Wednesday. And then test 2 is the week after that on Monday. And I eliminated the review for test 3, the class where we review for test 3. But on the Friday before the test, I will stay for the afternoon if anybody wants to ask questions or anything. We can have a little review session in here Friday afternoon if you need it. All right. So we want to review quickly what we have studied so far in terms of series by looking at the sheet that I gave you that says tests for convergence of infinite series on the top. Open this real quickly. Hello. There we go. Okay, so we have studied the first 4 tests for convergence. So we can look at a series and know that if it's geometric, that means that there's a constant multiplier to get from term to term. And if that constant multiplier is less than 1, the series converges. And if it's bigger than or equal to 1, it diverges. And we even know what it converges to, right? The a over 1 minus r. We called it x before. Some people call it r. Then we have a p series. Anytime you have the sum of 1 over n to the p, if p is bigger than 1, it converges. Less than or equal to the 1, it diverges. Just like the integrals. Same rules for integrals. And then we had a test for divergence that we talked about. You can use this for any series. And it just says that if the terms don't go to 0, the series diverges. Okay, so that's all it tells you. It tells you nothing if the terms do go to 0. It could still converge or diverge. Right? But if the terms don't go to 0, there's no chance of convergence. And then we talked about the integral test. That's the last thing we talked about. If f is a positive decreasing function, the sum does whatever the integral does. And Emily actually brought up the comparison test last class, and we talked about it very briefly, and we're going to talk about it more today. So today, we're going to talk about a few more tests for convergence. So think of a series. When you're looking at an infinite sum, infinite series, think of that series as a patient, and you were a doctor trying to diagnose it as convergent or divergent, right? And you will run several tests. Sometimes the tests are inconclusive, and you move on to the next test, right? So it's not always clear which test is going to give you good information, so you just keep trying tests until you get something conclusive. So we're going to learn lots and lots of tests. Well, not lots and lots. I don't know, 6 or 7 or so. And those are tools that you have to try to diagnose convergence or divergence. Okay, so the first of our tests that we're going to learn today is the comparison test. It's very similar to the comparison test for integrals that we studied earlier in the semester. You can compare these 2 tests later to try to figure out the similarities. So if I want to figure out whether this series converges, the sum of 1 over 3 to the n plus n. All right, so I'm going to look at a similar series that I happen to know its convergence or divergence. Okay? So I want to consider a similar series, the sum from n equals 1 to infinity of 1 over 3 to the n. A similar but simpler series whose convergence or divergence I know, right? That sum, does it converge or diverge? It converges. How do you know? Okay, the terms go to 0. That means it has a chance of convergence. So how do you know that it definitely converges? Yes, fantastic, Sephora. This is a geometric series. If you were to write out the terms, we'd have a third plus a ninth plus a 27th, right? This is geometric because every term is 1/3 the term before it. 1/3 times the term before it. So this converges because it's geometric. And the multiplier, we'll call that, we've been calling it x, so I'll call it x, is 1/3, which is less than 1. Okay, so we know this converges. So I have a sum that's similar to the sum I'm interested in that I know converges. Now, if you look at 1/3 to the n plus n, any term in this, no matter what I plug in for n, how does that fraction on the left compare to 1/3 to the n? It's smaller because my denominator is going to be bigger, right? Whatever 3 to the n is, they have that in common, and then I'm going to add something to the denominator. Denominator is going to be bigger, the fraction will be smaller. So every term in this series that I'm interested in is smaller than the terms in this series that I know converges. So this sum has to be smaller than that convergent sum, so it's also convergent. That make sense? If you show that a sum is smaller than another convergent sum, it has to also converge. Because being smaller than something finite implies that it's also finite. It's okay? All right, let's look at the next one. Similar, right? It's not, but instead of 1/3 to the n plus n, it's 1/3 to the n plus 1/n, and then these are different, right? Yeah, because if I wanted to add these two fractions, I would have to get a common denominator, and I would not get the thing in the other one. So this is totally different. I'm going to compare it to another series that's simpler, whose convergence or divergence I know. Okay, so I'm going to compare this to the sum of 1/n, which we know diverges. And then I'm going to look at my sum, the terms of my sum. The terms of my sum are always going to be bigger or smaller than the terms of 1/n. Bigger, because they have this 1/n in common, and then I'm adding something to 1/n. And this amount that I'm adding is some positive amount, right? It might be small, but it's some small positive amount, which means that the left side of this statement is bigger. So this is bigger than 1/n. And if the sum of 1/n is infinite, this sum would have to be bigger than it, which means that this sum diverges. So those are the two kinds of ways you can use a comparison test. Show that your sum is smaller than something that converges, or bigger than something that diverges. Smaller than something that converges, or bigger than something that diverges. So smaller than something finite, or bigger than something infinite. All right, what if I try to use the comparison test on n over 2n squared plus 1, that sum? I might consider comparing it to the sum. Well, I'm thinking, because I'm going to start plugging in really, really big n's into here, eventually my terms are going to start just looking like n over 2n squared, because those other two terms will be less significant. And n over 2n squared would reduce to 1 over 2n. So I'm going to compare it to 1 over n. Right? A simpler series whose convergence or divergence I know. That seems related to this guy. My hypothesis is that this is going to have the same behavior, convergence or divergence, as this. Okay. So I'm going to try to use a comparison test, right? Which means that I need to show that the terms of my sum are bigger than this, bigger than the terms of 1 over n. So let's write this out. If I have n over 2n squared plus n plus 1, I want to compare this to 1 over n, which is a difficult comparison to make because the numerators and denominators are different. Mm-hmm. Yeah, the denominator is bigger. The numerator is bigger too, so it's hard to tell. So if you just do a little trick and make the numerators the same, right? That's what I had on your test. So now the numerators are the same, right? 2n squared plus n plus 1 is bigger than n squared, which means that this fraction on the left will be smaller, which doesn't tell me anything, right? Being less than something infinite does not tell me that it's finite or infinite. This is inconclusive. So you're a doctor and you're trying to diagnose this series. You just ran a comparison test. It came back inconclusive. So you have to move on to some other test, right? So this is inconclusive because less than infinity does not imply anything, right? And it does not imply infinite. So you can't make a conclusion here. It is possible to be smaller than infinity and still be infinite, and it's possible to be less than infinity and be finite. So I'm still pretty convinced, just from intuition, hopefully you are too, that this sum is going to behave the same as 1 over n. I'm just thinking that the lower order terms aren't going to matter much. When you start plugging in really big n's, it's going to have the same behavior as 1 over n. So the comparison test doesn't help us though. So to show that two series behave the same in terms of their convergence, we can take a limit comparison test. So we take the limit as n goes to infinity. Take the terms of one of your series over the terms of your other series. So you're comparing them by taking a ratio. So I'm going to have n over 2n squared plus n plus 1, and then all of that divided by the series I want to compare it to. Okay. Now, if this limit comes out to be a finite number and not 0, some finite number, but not 0, then that shows us that the numerator and the denominator are closely related. Right? Closely enough related that they have the same convergent behavior. They either both converge or both diverge. They do the same thing in the long run. So when I try to take this limit, I get the limit as n goes to infinity. I'm just going to do some simplification here. And then flip and multiply. So I have n squared over 2n squared plus n plus 1. And what is that limit? When n gets really large, 1/2, yeah. So when n gets really large, think about, you know, a quadrillion, trillion, billion, gajillion, right? When you square that number, it's going to be a quadrillion, trillion, billion, gajillion times as big as the original, right? Because you're multiplying it by itself. So it's so much bigger than itself when you square it that all the terms of lower order can be ignored, right? Those are so much smaller in comparison that they're like tiny, insignificant. So this becomes, when you take the limit as n goes to infinity, you can drop off all the lower order terms, and we just have n squared over 2n squared, and the n squareds cancel, and you get 1/2. So the shortcut, if you remember from pre-calc when you do horizontal asymptotes of rational functions, you can just look at the ratio of the leading terms if the degrees are the same. So it's 1/2. All right, that number being finite and non-zero lets us conclude that the terms of this sum and the terms of this sum are alike enough that the convergent or divergent behavior of the two series will be the same. So since we know 1/n diverges, this test tells us that this one also diverges. So 1/2 finite and non-zero. Our conclusion is that the sum of 1/n and the sum of n over 2n squared plus n plus 1 both do the same thing. They either both converge or both diverge. And I know that this one diverges, so they have to both diverge. Oh, no, you can just do that because this is always almost always the same. So you can, I'd leave it off sometimes. So here's the formal statement of the limit comparison test. If all your terms are positive, so this only works if every term of your series is positive, well, beyond a certain value. You can have a finite number of negative ones. If the limit of the terms of one series over the terms of the other series is finite and not zero, then both of these sums do the same thing. They either both converge or both diverge. So here's a pair of series, 1/5n and 1/n squared. We already know one of them diverges and one of them converges, right? We talked about p series last class. So 1/5n, that's going to diverge. 1/n squared, that's going to converge. So I just want to show you that if you try to do the limit comparison test on these, it's not going to give you a finite non-zero number. Okay, so I would take the limit as n goes to infinity. One of my series, 1/5n, divided by the other, 1/n squared. So this is 1/5n times n squared over 1. So that becomes n/5, and that limit would be infinite. And if you flip it around, it'll go to 0. So if I compared them in the other order, you'll get 0. Yeah. So in these two instances, your results are actually inconclusive, right? You can't conclude that they have opposite behavior. It just says they don't necessarily have the same behavior. Inconclusive. Okay, so you know that if you get a finite non-zero number, they have the same behavior. But if you don't, if you get infinity or if you get 0, it's inconclusive and you have to move on to another test. I like this analogy of medical testing because there are certain tests that if it comes back positive, you can be pretty confident that you have whatever the thing is. But if it comes back negative, there's actually a lot of false negatives, and getting a negative means you should move on to another test just to double check. All right, so I would like you to try the limit comparison test on n squared over 2 to the n. But we need to decide what to compare it to, right? What would be a series that's simpler than that, but whose convergence or divergence we know? Nothing? What about 1 over 2 to the n? Does that converge or diverge? Converges. So if I do a limit comparison test where I compare this guy to this guy, if I get a finite non-zero number, I'll know that they both converge. Yeah, it's a little bit random, not completely. Yeah, it's going to be related to this somehow. Yeah. How are they related? They've got the same denominator. That's all. Which is infinite. Yeah. Yeah. So take the limit as n goes to infinity. The terms of one of my series is n squared over 2 to the n. Divide by the terms of my series whose behavior is known, 1 over 2 to the n. Simplify this, and you end up with the limit as n goes to infinity of n squared. Right? And that's infinite. So I'm inconclusive. So I could try to come up with another series. Maybe, I don't know, n squared? Yeah. The sum of n squared diverges, right? If you just add bigger and bigger numbers, 1 plus 4 plus 9, that's going to diverge. So I could compare it to n squared, and I would say, okay, take the limit as n goes to infinity of where the n squareds cancel, and I have 1 over 2 to the n, which is 0, still inconclusive. Okay, so it's about time to give up on the limit comparison test for this particular series. We're not getting good information from it, so we want to try another test. This is called the ratio test. It is for series that are similar, that are almost geometric. This test shows a series is almost geometric. So in a geometric series, if you take any two successive terms and divide them, you always get the same number. So let me just do an example of a geometric. So like if I have a half plus a fourth, an eighth plus a 16th, that's a geometric series, right? So if I take any two successive terms and divide them, 1/16 divided by 1/8, what do I get? One half. Any two successive terms. If I do an 1/8 divided by a 1/4, I get a half. Right? This is the definition of a geometric series. When I explained it to you the first time, I said it has some constant multiplier, right? To get from term to term. This is the same thing. If you take any term and divide by the one before it, you get that constant multiplier. Okay, so a series can be almost geometric if it's not always the case where if you divide two successive terms, you get the same number. But it might be the case where that happens if you go far enough out in the list. Right? If you write out enough terms that eventually every term divided by the one before it gives you the same number. So the ratio of successive terms is approaching a limit. And it's got the same, almost the same rule as geometric series. If that ratio is less than 1, you get convergence. Bigger than 1, you get divergence. And equal to 1, it's inconclusive. With a geometric series, equal to 1 shows divergence. But in this case, it's inconclusive. So let's go back to this series that I was trying to do with the limit comparison test, and we kept getting inconclusive results. Now I'm going to use the ratio test. So the ratio test says take the limit as n goes to infinity of the n plus first term divided by the nth term. So what's written here is a generic formula for the nth term, right? So the n plus first term would be n plus 1 squared over 2 to the n plus 1. That's the n plus first term. I just replaced all the n's in this formula with an n plus 1. And then I'm going to divide by the nth term, n squared over 2 to the n. And I forgot to write limit. Limit as n goes to infinity of that. All right, so this is the limit as n goes to infinity. I'm going to square that thing, and I get n squared plus 2n plus 1 over 2 to the n plus 1. And then I'm going to take this fraction that I'm dividing by and flip and multiply. So this becomes times 2 to the n over n squared. I want you to look at these two guys. What does 2 to the n over 2 to the n plus 1 reduce to? 1/2. Great. Let's explain why. 2 to the n over 2 to the n plus 1. Just think about the definition of an exponent, right? 2 to the n means 2 times 2 times 2 times, got n of those, right? Multiply n 2's together. 2 to the n plus 1 means 2 times 2 times 2 times 2, that's n 2's, times one more 2. And then whoosh, whoosh, and you get 1/2. Make sense? So go back over here. And I now have the limit as n goes to infinity of n squared plus 2n plus 1 over 2n squared. So all I did was simplify the 2 to the n over the 2 to the n plus 1. And then what is that limit? 1/2. Yep. And that is less than 1, which means my series converges. Ready for the next one? Not quite, okay. Okay, so if I want to use the ratio test here, that says take the limit as n goes to infinity of the n plus first term over the nth term. So the n plus first term means replace all your n's with n plus 1's in the formula. So this becomes 4 to the n plus 1 over n plus 1 factorial. and then divide by the nth term, which is just the given formula. So the first thing I'm going to do is my flip and multiply. This is 4 to the n plus 1 over n plus 1 factorial times n factorial over 4 to the n. All right, so we already saw how to reduce these two guys, right? I'm going to be left with a 4 on top when I cancel those two. This is n plus 1 4s, this is n 4s, cancel them, and you'll have 1 4 left on top. So I have 4 times n factorial over n plus 1 factorial. Yeah, it would just be n plus 1 on the bottom. Let's write that out. Explain it. So I have n factorial divided by n plus 1 factorial. Well, n factorial means 1 times 2 times 3 times 4 times up to n. Stop at n, right? N plus 1 factorial means 1 times 2 times 3 times 4 times n times n plus 1. Stop one more than that. And then you get whoosh, whoosh, cancels, and you just have an n plus 1 on the bottom. No more exclamation point. So this is now the limit as n goes to infinity of 4 over n plus 1. So it canceled all the factors of the factorials. And what is that limit? As n goes to infinity, 4 over n plus 1 goes to 0. Right. Now, in this test, all we care about is if that limit is less than 1. Right? It's hard to keep track of the rules, I know. Because in the previous test, the limit comparison test, 0 was an inconclusive result. In this test, 0 is fine, right? You say this is less than 1, oops, we can conclude convergence. I know it's hard to keep track of, that's why I made this special little sheet for you. So you can look and say, okay, I'm doing the ratio test. I just need to see if the ratio of the terms is less than 1. And in the last column, this tells you nothing if it equals 1, right? 0 is not a problem. 0 is less than 1. So we know it converges. Yeah. According to the pattern of the lesson, this test isn't going to work for the last one. But I still would like all of you to try it. Figure out what the limit as n goes to infinity of the n plus first term over the nth term equals. And I'll give you a few minutes to do that. All right, so let's go through this tedious calculation together. This is going to be the limit as n goes to infinity of n plus 1 over, all right, I'm going to simplify this 2 times n plus 1 squared plus n plus 1 plus 1 and flip and multiply in this same step. So when I square n plus 1, I get n squared plus 2n plus 1. And when I distribute my 2, I'm going to have a 2n squared. And then I'm going to look at my n terms. I have 2 times 2n is 4n, plus this n here is 5n. And then in squaring the n plus 1, I get a 1. Distribute the 2 and I get 2, plus another 1 is 4. So that's just the denominator multiplied out and combined like terms. Okay, so then I'm dividing that fraction by another fraction. So I'm going to flip it and multiply it, and this becomes 2n squared plus n plus 1 over n. Okay, so now to simplify this product, to multiply two fractions, you multiply the tops and you multiply the bottoms. So I have to multiply n plus 1 times 2n squared plus n plus 1, which is going to be long and tedious, right? You got to distribute the n to every term, and then you got to distribute the 1 to every term, and then you got to combine like terms. But the result, I know, is going to be a polynomial. And it's going to be what degree polynomial? Cubic, yeah. What's the leading term going to be? 2n cubed. The 2n squared times the n, that's going to be the highest degree term I get. So I'm going to have 2n cubed plus a bunch of lower order terms, which when I take the limit as n goes to infinity aren't going to really matter. Okay, and then in my denominator, distributing this n to 2n squared plus 5n plus 4, my highest degree term is going to be a 2n cubed, plus a bunch of lower order terms that don't really matter when I take the limit. And so the limit as n goes to infinity of 2n cubed over 2n cubed is 1. So this test is inconclusive. So it's a lot of work for nothing. Especially when we already know that this diverges because we looked at this sum earlier in class. Yeah. Okay, so the moral of the story for the ratio test. Try the ratio test for series that involve quotients of factorials, exponentials, and powers. Don't bother with it if you have a quotient of polynomials. The limit will always be the dreaded 1. It takes a lot of experience to recognize when to use which test. So use the sheet I gave you, and just think about it as trying to diagnose something, right? You're a doctor, you're trying to diagnose this series as convergent or divergent. You have lots of tests available to you. Some tests work better on some patients, right? So if you know your patients because you have a lot of experience and you say, oh, I've seen lots of patients like this guy, then you'll know what test to use. And until you have that experience, you might just have to try lots of tests, right? And you might just have to do a lot of them. So expect to make some false starts. Expect to pick some tests that tell you nothing until you gain some experience. And even then, you'll still do it every once in a while. All right, so I have a couple of problems for you to try. I do have the answers on the next page, but try to do these without looking at them first.